Tonight, the most dangerous asteroids in our solar system are not the biggest names in headlines, but the real objects astronomers watch with quiet precision. Some pass safely, some once seemed threatening, then faded with better data. And a few still remind us that Earth moves through a far less empty system than it seems. In this video, the story follows where real impact risk begins, how it is measured, and why early warning may be the only thing standing between a distant rock and a future disaster. If this kind of deep space documentary is worth watching, please like the video, subscribe to the channel, and join for more calm journeys through the universe. Far beyond Earth, beyond the crowded region of the inner planets, and beyond the familiar paths of daily astronomy, the solar system holds a quieter landscape of stone, metal, dust, and long memory. This is where the story of dangerous asteroids begins. It does not begin near cities or oceans or skies lit by fire. It begins in distant sunlight, among ancient bodies that circle the sun in enormous numbers and usually do so without drama. The most important of these source regions lies between Mars and Jupiter, in the main asteroid belt, where countless rocky bodies travel on separate paths around the Sun, from a distance. The phrase asteroid belt can suggest a tight, packed ring of drifting rubble, but the real region is much more spacious and much more still. Individual asteroids are usually separated by vast distances. Most never come close to one another. Most never come close to Earth. They remain where they have circled for ages, dim and cold and only slowly changed by time. This broad region preserves some of the oldest surviving material in the solar system. The large planets, the moons, and the smaller worlds all emerge from the same early disk of gas and dust that surrounds the young sun. In the main belt, some of that ancient building material remains in bodies that never joined together into a full planet. Jupiter plays an important role in shaping this outcome. Its strong gravity stirs the region and prevents the rocky material there from settling into one larger world. As a result, the belt becomes a long-lived archive of unfinished formation. It contains objects of many sizes, from the dwarf planet Ceres, which is large enough to become rounded by its own gravity, down to small fragments little larger than boulders. Between those extremes lies a rich population of bodies with different compositions, different histories, and different surfaces, each carrying part of the solar system's earliest record. The outer source of real impact risk, therefore, does not appear, at first, as a place of menace. It appears as a place of preservation. Many asteroids in the main belt are primitive, which means they remain chemically close to early solar system material. Some are rich in carbon-bearing compounds and darker than coal. Some are stonier and brighter. Some contain larger amounts of metal. Their variety matters because the dangerous asteroid is not a special class born in isolation. It emerges from this wider population of ordinary small worlds. The rocks that one day may matter greatly to Earth are first only members of a much larger family, circling the sun in relative silence. The main belt is not the only distant reservoir of asteroid danger, but it is the clearest and most important one. Beyond it lie other small body populations, including groups that share space with planets or occupy more distant and less familiar regions. Yet the main belt remains the central storehouse of the rocky bodies most often discussed in planetary defense. It is the middle archive of the solar system, neither as close as the terrestrial planets nor as remote as the icy outer domains. It occupies a region where sunlight is weaker than at Earth, but still strong enough to warm exposed surfaces by day and cast long, sharp shadows over cratered ground. In telescopes, the larger members appear as tiny moving points, spacecraft reveal something more textured, scarred surfaces, broken shapes, rubble-strewn terrain, and bodies that preserve collisions billions of years old. Collision is part of the belt's long history, though not in the constant violent sense often imagined. Over immense spans of time, asteroids do strike one another. Larger bodies fracture, smaller bodies shatter. Families of related fragments spread through nearby orbital space. Some asteroids are therefore not primordial survivors in their present form, but the products of older impacts. Even this process, however, unfolds with great patience. The belt is not a storm. It is a vast field of separated objects, occasionally altered by contact, mostly governed by orbit. The danger later associated with asteroids is born from this calm setting. It grows out of age, abundance, and persistence, not from immediate chaos. There is something unsettling in that contrast. The most dangerous asteroids in the solar system are not usually born in spectacular events visible from Earth. They begin as members of a distant, ordinary population that spends most of its existence unnoticed. Their true origin lies in deep time. They inherit their matter from the early solar system, their shapes from slow accretion or ancient breakage, and their surfaces from long exposure to sunlight, micrometeorite impacts, and the vacuum of space. Some are solid and coherent. Some are loose collections of fragments held together by gravity, often called rubble piles. Some spin slowly, some rotate more quickly. All remain part of a much wider small body environment that usually seems detached from human life. This outer region also corrects a common instinct about danger. The dangerous asteroid is not usually the biggest object in the belt, nor the brightest, nor the easiest to notice. The belt contains giants compared with the bodies that would later concern Earth. Ceres, Vesta, Pallas, and Hygeia dominate much of its total mass. Yet real impact risk does not begin with simple size alone. It begins with membership in a reservoir that contains many kinds of objects, including far smaller ones that may one day matter more. The main belt is therefore less like a gallery of famous worlds and more like a deep background population from which future threats can arise. From the widest outer view, this is the first truth of the subject. The solar system keeps its dangerous asteroids in ordinary places. It stores them among ancient remnants, in broad zones of quiet sunlight, where they circle the sun as part of the natural architecture left behind by planetary formation. The main belt is not a frontier of constant violence. It is a patient reservoir, sparse in spacing, immense in age, and rich in material that has remained in motion since the earliest history of the Sun's family of worlds. The danger attached to some asteroids later on does not erase this deeper identity. It depends on it. Before any asteroid becomes a real impact risk, it exists here first as one small body among many, moving through a distant region that seems calm, stable, and almost indifferent to the inner planets. The distant reservoirs of asteroids do not remain completely sealed from the inner solar system. Their populations appear calm when viewed on human timescales, but over far longer spans the orbits of some bodies slowly change. This quiet change is the next layer in the story of real impact risk. A dangerous asteroid does not usually begin as a special intruder already aimed at Earth. It begins as one member of a larger population whose path is gradually altered until it drifts inward. The process is slow, often delicate and deeply shaped by gravity, sunlight, and time. In the main belt, each asteroid circles the Sun on its own route, but that route is never perfectly isolated. The large planets, especially Jupiter, exert a steady gravitational influence across the belt. Most asteroids remain on long-lived paths that avoid serious instability. Yet some occupy regions where repeated gravitational timing creates trouble. This timing effect is known as resonance. A resonance happens when an asteroid and a planet complete their orbits in a simple numerical pattern, so that the planet's pull returns again and again at nearly the same point in the asteroid cycle. The individual tug is small, but repetition matters. Over immense stretches of time, the repeated pull can reshape the orbit. In the main belt, such resonances open routes out of the reservoir. Certain bands become depleted because asteroids placed there tend not to remain there forever. They're gradually nudged into more stretched paths, with orbits that carry them farther inward or farther outward than before. Astronomers see the result in the Kirkwood gaps, which are regions of the belt where fewer asteroids are found because resonances with Jupiter destabilize those orbital zones. These gaps are not empty tunnels in any physical sense. They are patterns in orbital space, signs that some routes through the belt are less stable than others. For the asteroid that enters such a route, the belt becomes less of a home and more of a passage. Jupiter is not the only influence. Mars also plays a role near the inner edge of the main belt, where its gravity can help perturb the paths of smaller bodies. Saturn contributes indirectly through its broader effect on the architecture of the solar system. Even the combined gravitational field of the planets, acting in subtle ways over long intervals, helps create a dynamical environment in which some asteroids are gradually loosened from the populations where they began. The important point is not sudden ejection, but accumulated change. The inward drift corridor is not a dramatic launch. It is a long erosion of orbital stability. Sunlight adds another quiet force. When an asteroid absorbs sunlight and later releases that energy as heat, the re-emitted heat can create a tiny thrust. This is called the Yarkovsky effect. It is very weak, far too small to matter over a day or a year in any ordinary way. But an asteroid may circle the Sun for millions of years. Over such spans, a persistent force this small can slowly shift the size of an orbit. The direction of the drift depends on how the asteroid spins and how its surface warms and cools. A small body rotating in one sense may drift gradually inward. Another rotating differently may drift outward. The effect is strongest for smaller asteroids, because their low mass makes them easier to move. In this way, sunlight itself helps feed the resonant escape routes. This is one of the quietest and most important truths in asteroid science. A rock in space does not need an impact or a close planetary encounter to begin moving toward danger. It may simply spin under sunlight for millions of years, losing and re-radiating heat, until its orbit shifts enough to enter a resonance. Once inside that unstable zone, gravity takes over more strongly and can increase the stretching of the orbit. The asteroid then becomes more likely to leave the main belt altogether and enter the family of bodies that travel deeper into the inner solar system. These corridors do not move great numbers of asteroids at once. The belt remains the belt because most objects do not fall inward on short timescales. The transfer is selective and gradual, yet the population is so large, and the solar system is so old, that even a small leak is enough to supply the near-Earth population over time. The inner solar system does not need a flood of incoming bodies to create real hazard. A steady trickle across millions and billions of years is sufficient. That is why the dangerous asteroid can be both rare in the immediate sense and inevitable in the long historical sense. The corridor remains open, even when no single body within it seems urgent. As an asteroid begins this journey, its path changes character. In the main belt, its orbit may once have remained mostly confined between Mars and Jupiter. After enough drift and enough resonant shaping, that orbit can become more elongated. The asteroid may begin approaching the path of Mars. Later it may reach farther inward. Each step does not guarantee eventual closeness to Earth, but the direction of change is important. The object has left the quiet stability of its reservoir and entered a population with more mobility, more planetary interaction, and more potential for future encounters. The corridors are therefore not places in the ordinary spatial sense. They are processes written into the mechanics of the solar system. They consist of orbital relationships, thermal effects, timing, and the slow reworking of motion. Nothing visible marks them like roads through a landscape. A telescope does not see a lane of glowing stone leading sunward. Science infers these routes from the observed distribution of asteroid orbits, from computer models, and from the measured properties of individual bodies whose motions reveal tiny long-term changes. The result is a picture of constant but patient transport from distant reservoirs toward the inner regions. This transport is what makes the wider asteroid population relevant to Earth at all. Without these inward corridors, the main belt would remain mostly a remote archive, rich in history, but poor in consequence for the inner planets. With them, it becomes the source of a continuing supply of bodies whose orbits can evolve into something more consequential. The danger still lies far ahead of any one object at this stage. It is not yet written as impact. It is written only as access. A route exists. The solar system allows certain rocks to drift, to enter unstable orbital zones, and to leave their long-held places. So the calm outer reservoir is not fully closed. It leaks by the quiet action of physics. Gravity repeats its small tugs. Sunlight applies its minute thermal push. Orbital paths slowly deform. Unstable regions remove some object from old patterns and guide them inward. The most dangerous asteroids in the solar system begin their approach in this patient way, not with spectacle, but with long mechanical persistence. The corridor inward is real, ancient, and always in operation, carrying a small fraction of distant bodies away from the broad stillness of the belt and toward the deeper reaches of the Sun's domain. Once an asteroid leaves the distant reservoirs and enters the inner solar system, it joins a different family of motion. It is no longer defined mainly by its place in the belt beyond Mars. It becomes part of the near-Earth population, a shifting collection of small bodies whose paths bring them into the neighborhood of Earth's orbit. This does not mean that each one is dangerous. It means only that the object now belongs to a more intimate orbital environment, where the inner planets matter more and distance from Earth is measured differently. The change is not one of appearance. Most near-Earth asteroids still look like faint points of light in telescopes. The change is one of geometry. Their danger begins to be discussed not because they shine more brightly, but because their orbits reach into the region where Earth moves. Astronomers organize these asteroids into families based on the shape and size of their paths around the Sun. This classification is useful because orbit determines relationship. A rock does not become important to Earth because of color, because of texture, or because of the exact shape of its surface. Those properties matter later for understanding composition and physical response. But the first sorting principle is simpler. The crucial fact is how close the asteroid's orbit comes to the Sun, how far it extends outward, and whether that path remains mostly inside Earth's orbit, mostly outside it, or stretches across it. In this way, the near-Earth families form a map of possibility. One family consists of asteroids whose entire orbits lie within Earth's orbit. These are sometimes called the innermost near-Earth asteroids. They remain close to the Sun from Earth's point of view, and are therefore difficult to observe. The geometry of their motion keeps them in bright twilight or daylight skies, hidden in the direction of the Sun rather than displayed against the dark night. Their importance lies partly in this concealment. An asteroid can belong to the near-Earth population and still remain hard to discover simply because its orbit keeps it in a region of the sky that telescopes on Earth do not search easily. These inner bodies show that nearness is not the same as visibility. A nearby orbital family can remain poorly known for a long time because the geometry of observation works against it. A second family includes asteroids whose orbits are smaller than Earth's overall but still reach outward, far enough to cross the path of Earth from the inside. These bodies move on comparatively tight paths around the Sun and complete their years more quickly than Earth does. Because they spend much of their time closer to the Sun, they can approach Earth from directions that make detection difficult until careful surveys catch them. Their motion reveals an important truth about orbital risk. A smaller orbit does not mean a safer one. An asteroid can live mostly inward of Earth and still enter the same region of space at certain times. The scale of its orbit matters, but the extent of that orbit matters more. Another major family contains asteroids whose paths are larger than Earth's orbit overall, but whose inner reaches dip inside it. These are among the most numerous and most familiar of the near-Earth groups. They spend much of their time farther from the Sun than Earth does, then sweep inward along elongated paths. Their years are longer, their changing speed along the orbit, faster near the Sun and slower farther out, gives their motion a broad rhythm that differs from Earth's own. This family is especially important because it shows how the stretching of an orbit transforms a once remote body into a repeated visitor to the inner solar system. The path does not need to resemble Earth's, it only needs to overlap the same general zone around the Sun. Elongation, not likeness, creates the relationship. There is also a family whose orbits approach Earth's from the outside without crossing it. These asteroids come close to the path of Earth, but remain just beyond it. They are near-Earth asteroids because they enter the neighborhood of the planet's orbit. Yet their geometry keeps them on the outer side. This family is scientifically important because it forms a borderland between quieter motion and more consequential motion. An asteroid can belong to the near-Earth population without becoming an immediate impact concern. It may remain outside Earth's path while still passing close enough in orbital terms to deserve attention. This is why the category near-Earth asteroid is broader than the category of true hazard. It marks a neighborhood, not a verdict. Seen together, these families reveal that the near-Earth population is not one uniform swarm. It is a layered system of orbital styles. Some asteroids remain mainly inside Earth's orbit. Some cross outward from within. Some fall inward from beyond. Some only approach from the outer side. Their differences are not decorative. They shape how often an asteroid can be observed, how strongly planets can perturb its motion, and how its long-term future may change. The same rocky body may spend ages in one family, then later move into another as gravitational encounters slowly alter its path. The families are therefore both categories and stages, ways of describing the current arrangement of motion within a population that keeps evolving. This is where real danger begins to take a recognizable form, though not yet a final one. The first step toward danger is not size alone. It is not the name of the object. It is not public attention. It is the simple fact that an orbit has entered Earth's broader neighborhood. Once that happens, the asteroid belongs to a family defined by proximity of motion rather than distant origin. It may still be harmless. It may remain so for a very long time. But the solar system now treats it differently. The inner planets become regular influences. Earth is no longer remote from its path. The language of risk becomes possible because the language of orbital kinship now applies. So the near-Earth families serve as a kind of orbital census. They describe how asteroids live near Earth without yet deciding which ones truly threaten it. That distinction matters. A near-Earth asteroid is not automatically dangerous, just as a distant main belt asteroid is not automatically irrelevant. The families only show how motion has changed. They record the gradual inward migration of certain bodies and sort them by the reach of their paths around the Sun. In this orbital landscape, danger begins quietly. It begins when a distant rock becomes a local one, when its route enters the same inner domain that Earth inhabits, and when the architecture of the solar system brings two worlds into related motion around the same star. Among the near-Earth asteroid families, the most consequential paths are those that do more than approach the neighborhood of Earth. They pass through it. An Earth-crossing asteroid is one whose orbit around the Sun intersects the orbital path of Earth in a real geometric sense. This is where the subject of impact risk becomes sharper, though it still remains quieter and more conditional than public imagination often assumes. The crossing itself does not mean a collision is underway. It does not mean the asteroid and Earth arrive at the same place at the same time. It means that their routes through space overlap. The possibility of impact begins here because the geometry allows it. This distinction matters. Space is not a flat drawing, even though orbital diagrams are often shown that way. Earth and an asteroid both follow paths around the Sun, but they do so at particular times, with particular speeds, and often with particular tilts relative to one another. An orbit may cross Earth's path on paper and still produce no danger for a long interval if the asteroid reaches the crossing point when Earth is elsewhere. The solar system is full of such near misses in principle, where one body travels through a location that another body occupies only at a different time. Risk emerges not from crossing alone, but from crossing combined with timing. Even so, the crossing is the essential first condition. Without it, the geometry of impact is absent. The Earth-crossing population therefore occupies a more serious orbital class than the near-Earth asteroids that only approach from inside or outside without intersecting Earth's route. These crossing bodies are allowed by their motion to enter the same annular region around the Sun that Earth occupies. Some do so from smaller orbits that stretch outward. Some come from larger orbits that dip inward. The direction matters less than the overlap. Their paths are elongated enough, or arranged in such a way, that Earth's orbital zone is no longer separate from their own. The two routes now belong to a shared corridor around the Sun. Yet this shared corridor is still wider and more layered than instinct suggests. Earth itself is not a point moving on a line. It is a planet with size, gravity, and a path that changes position continuously through the year. The asteroid is also not a point in the practical sense of hazard, because if a close approach occurs, Earth's gravity can slightly alter the path even before any impact becomes possible. In addition, many asteroid orbits are inclined, which means they travel above or below the plane of Earth's orbit for part of their circuit. A crossing drawn from above may therefore look more direct than it really is in three-dimensional space. The orbit can intersect Earth's orbital distance from the Sun while still missing Earth by a vertical margin. This is why real impact analysis depends on careful orbital calculation rather than simple visual sketches. Astronomers often describe the closeness of an asteroid's orbit to Earth's orbit by using measures of minimum orbital separation. These values help identify which objects deserve closer attention. They do not guarantee future impact. They show how closely the paths can approach one another if timing and position line up in a certain way. In practice, the Earth-crossing population contains a wide range of situations. Some bodies have orbits that cross in a relatively mild way, with only narrow overlap or with a strong tilt that reduces actual encounter likelihood. Others pass through Earth's orbital space more directly and more often. The crossing is therefore not one simple condition, but a spectrum of orbital intimacy. Repeated return is a crucial part of the danger. An asteroid that crosses Earth's orbit does not usually get only one chance to matter. If the orbit remains stable enough, the body returns again and again, each solar year or every few years, depending on the size and shape of its path. Every return creates another opportunity for Earth and asteroid to arrive at a similar region of space at the same time. Most such opportunities produce nothing beyond a distant passage. Still, repetition changes the character of the risk. A crossing orbit is not a single event. It is a continuing relationship between two moving bodies whose paths allow future encounters as long as the geometry persists. This is one reason danger in asteroid science is often quieter than it appears in headlines. A real impact risk is usually not discovered as a rock visibly racing toward Earth in a final straight line. It is discovered as an orbit with a certain shape, a certain uncertainty, and a certain future pattern of close approaches. The risk belongs first to the path. The asteroid may be millions of kilometers away, calm in appearance, and still scientifically important because its orbit threads through Earth's domain. In that sense, the dangerous quality is not yet in the rock alone. It is in the repeated intersection of two celestial routines. Earth-crossing paths also make the influence of the planets more important. Once an asteroid begins passing through the inner solar system in this way, its future is less isolated. Encounters with Earth, Mars, or Venus can gradually alter its orbit. The object may remain Earth-crossing for a long time, or later be shifted into a different near-Earth family, or eventually be removed from the inner solar system altogether by impact, solar collision, or ejection into a new orbit. The crossing population is therefore dynamically active. Its members are not fixed in one eternal arrangement. They are bodies in transit through a region where planetary gravity can slowly rework their futures. From the standpoint of real impact risk, this is the first truly intimate region of the subject. The asteroid is no longer merely near Earth in a broad sense. Its path cuts across Earth's path. The overlap is physical, orbital, and repeatable. Still, the danger remains conditional. The crossing supplies permission, not outcome. Timing, inclination, future perturbations, and observational precision all continue to matter. The most dangerous asteroids are not simply the ones that cross Earth's orbit, but no asteroid can become a true impact threat without first belonging to this class of intersecting motion. So the Earth-crossing path marks the transition from neighborhood to direct orbital relationship. A distant reservoir supplies the body. Inward corridors bring it sunward. Near-Earth families define its new environment. Here, at the crossing itself, the geometry becomes serious enough to support real impact risk. The solar system does not yet promise collision, but it now allows it in a strict and recurring sense. That allowance is the quiet heart of asteroid danger. It is written not in brightness or drama, but in the shape of an orbit that returns again and again through the same region, where Earth makes its yearly passage around the Sun. Within the Earth-crossing population, astronomers apply another filter to separate general orbital interest from a narrower class of concern. This filter does not identify certain impact. It does not declare that an asteroid is on its way to Earth. It serves as a screening rule, a practical way of marking which objects deserve closer attention because of their size and the nearness of their orbital path to Earth's own path. The official term is potentially hazardous asteroid. The phrase sounds severe, and in ordinary language it easily suggests immediate danger. But in planetary defense it has a more careful meaning. It is a label of possibility, not a prediction of outcome. An asteroid enters this category through two broad conditions. It must be large enough that an impact, if one ever occurred, could cause significant regional damage, and its orbit must bring it close enough to Earth's orbit that future encounters deserve continued monitoring. These are threshold conditions. They do not measure the full complexity of risk. They do not weigh timing, future gravitational changes, or the certainty of the orbit in one instant. They simply mark the object as one whose combination of size and orbital proximity places it within the class that planetary defense programs watch with more seriousness. Size matters first because not every asteroid that crosses Earth's orbit represents the same physical threat. A very small object may enter Earth's atmosphere and break apart high above the surface, producing only a fireball or an airburst with limited effects. A larger asteroid carries more kinetic energy, which is the energy of motion. At the speeds typical of solar system impacts, even a modest increase in size can mean a large increase in destructive potential. For this reason, the potentially hazardous class is not intended for every small rock that wanders near Earth. It is meant for bodies large enough that an eventual collision would matter on the ground in a substantial way. Because most asteroids are discovered as faint points of reflected sunlight, their exact size is not always known at first. Astronomers often begin with brightness, then infer approximate size from that brightness by making assumptions about albedo, which is the fraction of sunlight a surface reflects. A dark asteroid reflects little light and can appear dim even if it is fairly large. A brighter asteroid can appear similar in a telescope while being smaller. This means the size part of the screening rule often begins as an estimate rather than a final measurement. The potentially hazardous label therefore carries some uncertainty from the start. It is designed to be conservative enough to catch relevant objects even when knowledge is incomplete. The orbital part of the label depends on how close the asteroid's orbit can come to Earth's orbit. This is commonly described by a measure called the minimum orbit intersection distance, which is the smallest distance between the two orbital paths if one compares their shapes in space. It is important to note what this does and does not mean. It does not say that Earth and the asteroid will actually be that close on any given date. It says only that the paths themselves approach one another to within a certain limit. The true position of Earth and asteroid along those paths still matters. Even so, a small minimum orbital separation is a warning sign that repeated future encounters are possible, especially if the object is also large enough to be consequential. This is why the potentially hazardous category is best understood as a screening device. It identifies asteroids that are large enough to matter and close enough in orbital geometry to deserve ongoing scrutiny. It does not rank them all as equally dangerous. Some potentially hazardous asteroids have extremely well-known orbits that rule out impact for many decades, or even for more than a century. Others are newly discovered and remain poorly constrained for a time, so their future positions carry wider uncertainty. Some pass close to Earth often, others only rarely enter a geometry of interest. The label groups them for attention, not for alarm. The public meaning of the word hazardous can therefore diverge sharply from the scientific meaning. In everyday use, a hazardous object is one that is actively threatening. In asteroid science, the term is more measured. It marks a body that belongs in a watch list because the ingredients for danger exist in principle. The object is large enough. The orbit comes close enough. That is all the label guarantees. This distinction is essential because many well-known asteroids that fall into this category pose no realistic impact threat in the near future. They remain classified that way because the category is based on physical and orbital characteristics, not on a current collision forecast. There is also an important practical reason for using such a broad filter. Planetary defense works best when it begins early, long before any object becomes a short-term concern. An asteroid discovered decades in advance can be tracked, refined, and understood with steadily increasing precision. Its size can be measured better, its spin can be studied, its shape and composition may become clearer through radar, infrared observations, or future spacecraft work. A screening category helps ensure that potentially important objects do not disappear into a sea of lesser cases. It gives observatories and analysis systems a way to sort large numbers of near-Earth asteroids into a smaller subset that deserves more persistent attention. This category also reveals the calm logic of real impact science. Danger is not treated as spectacle. It is handled as classification, threshold, and continued observation. The most important work begins not with panic, but with careful bookkeeping. Which bodies are large enough? Which orbits come close enough? Which uncertainties remain wide enough that more data matters? The potentially hazardous label sits exactly at that boundary between broad discovery and focused monitoring. It marks the point where an asteroid becomes more than one moving point among many, and enters the disciplined field of long-term concern. So this region of the subject is one of naming and restraint. The phrase potentially hazardous asteroid sounds final, but it is deliberately incomplete. It does not say dangerous now. It does not say impact expected. It says only that the object meets a screening rule based on size and orbital closeness, and that this fact makes it worth sustained watchfulness. In that sense, the label is both serious and modest. It acknowledges real physical potential without claiming more than the data allows. The dangerous asteroids of the solar system first become visible in this way, not as certain attackers, but as bodies whose basic properties place them within a class that science refuses to ignore. Once an asteroid is large enough to matter and close enough in orbital geometry to deserve attention, it enters a quieter and more mathematical region of planetary defense. Here the central task shifts away from origin and toward prediction. Observers take the measurements available in the present, define the range of future paths still allowed by those measurements, and test whether any of those paths intersect Earth on specific dates. This is the region of the moving risk lists, maintained by systems such as NASA's Sentry and ESA's impact monitoring work. These lists do not exist to dramatize danger. They exist to organize uncertainty. Every newly discovered asteroid begins with incomplete knowledge. Telescopes record its position against the sky on one night, then another, then perhaps several more. From those measurements, astronomers derive an orbit, but the orbit is never known with perfect precision at once. There is always some uncertainty because the object has been observed over only a limited arc of its path. A short observing arc is the span of time over which the asteroid has been tracked. When that arc is brief, many slightly different orbits may still fit the data almost equally well. The asteroid is therefore not represented by one exact future, but by a cloud of possible futures. This is where automated risk systems become essential. Sentry at NASA and the comparable monitoring work used by ESA take the measured orbit and its uncertainty, then project many possible future paths forward through time. These paths include the gravitational influence of the planets, because even a small difference in position during a future close approach can grow into a larger change later on. The goal is to test the full family of allowable futures and determine whether any of them pass through Earth at a later date. If none do, the object does not belong on a formal risk list. If some do, even with very low probability, the object may appear there until better observations narrow the uncertainty. This is why an asteroid can briefly appear on a risk list and later disappear without any dramatic event taking place in space. The change usually happens on paper first, in the mathematics of the orbit. Follow-up observations extend the observing arc, improve the measured path, and shrink the cloud of possible futures. As that cloud becomes narrower, the small fraction that once passed through Earth often drops away. The impact probability then falls to 0 for the dates under study, and the object is removed from the list. In this sense, the moving risk lists are not signs of failure or instability in science. They show the uncertainty first, then allow it to contract as new evidence arrives. A listed probability therefore needs calm interpretation. A non-zero impact probability does not mean that impact is likely in the ordinary sense. It means that among the currently allowed futures, a certain tiny fraction intersects Earth on a given date. Sometimes that fraction is extraordinarily small. Sometimes it looks larger for a brief time simply because the orbit is still poorly known and only a narrow set of solutions remains under consideration. Public language often treats any listed probability as a threat already in motion, but the scientific meaning is more restrained. The probability is a measure of present orbital uncertainty mapped onto future encounters. It is not a statement that the asteroid is visibly heading straight toward Earth. The lists also move because the solar system itself keeps reshaping future paths. When an asteroid passes near a planet, especially Earth, the gravity of that encounter can alter the orbit. For some objects, this creates future return dates that deserve special attention. A close pass may slightly deflect the asteroid into a new path that must be recalculated with high precision. This is one reason risk monitoring continues over long intervals. The central work is not only to follow where the asteroid travels now, but also to measure how repeated planetary encounters may modify later possibilities. Most of the time, the risk displayed remains very low. Earth lives within a natural background of impact possibility spread across vast timescales. But the individual cases that appear on monitoring lists are usually far below the level that would justify alarm. They attract attention because they are specific, named objects with dated possibilities, yet the numbers attached to them are commonly small and provisional. What matters scientifically is not that they appear frightening, but that they are measured at all. A real monitoring system does not wait for certainty. It tracks possibilities early, then reduces them with better data. The lists are also disciplined by transparency. NASA and ESA publish the monitored objects, the relevant dates, and the changing probabilities so that the process can be examined openly. This openness is important because impact risk is easy to misrepresent when removed from context. A single percentage or fraction can sound severe when detached from the uncertainties behind it. Within the monitoring systems, however, the number belongs to a larger structure. It depends on the quality of the observations, the length of the observing arc, the geometry of future encounters, and the gradual removal of incorrect orbital solutions. Seen this way, the list is less a catalogue of threats than a working ledger of unresolved cases. The most important lesson of the moving risk lists is therefore methodological. Planetary defense does not treat asteroid danger as a fixed picture discovered once and for all. It treats danger as a calculation that improves over time. The list moves because knowledge moves. New observations shift the orbit. Refined measurements reduce uncertainty. Some objects rise briefly in concern, then fall away. Others remain of interest for longer because their future encounters are more delicate, or their observations are slower to complete. Through all of this, the systems remain grounded in probability, not drama. So this region of the subject is one of disciplined uncertainty. Here the asteroid is defined by a set of possible futures being tested against Earth's future position. NASA's Sentry and ESA's risk monitoring systems stand in that narrow space between incomplete knowledge and clearer knowledge. They maintain moving lists because orbital certainty is earned, not assumed. Most listed cases diminish with time and better observation. All are handled in the same calm way by measuring the orbit, projecting its possible futures, and letting evidence steadily decide whether the danger is real or only a temporary shadow cast by uncertainty. Asteroid 2024, YR4, becomes an unusually clear example of how a real impact concern can briefly rise into public view and then fade as knowledge improves. It is not remembered chiefly because it was the most dangerous asteroid ever found. It is remembered because it reveals the normal pattern of early uncertainty in a form that many people can see almost day by day. The object is discovered in late December of 2024. After it has already passed its closest point to Earth on that approach, it enters the Planetary defense system as a newly found near-Earth asteroid with only a short observational record. That short record allows many future paths to remain possible at once. Some of those paths pass through Earth on a date in December of 2032. Because of that, the asteroid rises onto the formal risk lists used by NASA and ESA. At first the percentage is small, but not zero. Then, as follow-up observations continue, the estimated chance of impact briefly rises rather than falls. This can seem alarming from outside the scientific process, yet it is often exactly what happens when the first uncertain orbit is slowly narrowed. The object is not becoming more hostile. The uncertainty is becoming more concentrated. The early rise in concern comes from the way orbital uncertainty behaves. When an asteroid is first observed for only a short time, astronomers do not know its future path as one thin line. They know it as a band of possible paths. If Earth lies somewhere inside that band on a future date, then some fraction of the possible orbits lead to impact and most do not. As more measurements are added, the band becomes narrower. During that narrowing, the fraction of possible orbits that intersect Earth can briefly increase even though the total uncertainty is shrinking. This is one of the central lessons of 2024 YR4. A rising impact probability is not always a sign that impact is becoming genuinely more likely in the everyday sense. It can be a sign that the cloud of uncertainty is collapsing toward the truth, and that the truth has not yet fully separated from Earth. ESA later describes this rise and fall as a well-understood pattern, and the case follows that pattern closely. The asteroid reaches the top of ESA's risk list, and for a short time, its Earth impact probability climbs to around 3%, before additional data cut away most of the remaining impact solutions. The details of the object also help explain why it draws such attention. Official estimates place its size somewhere between about 40 and 90 meters, later refined by Webb observations to roughly the scale of a tall building. An asteroid in that range is not a civilization-ending body, but it is large enough that an actual impact could severely damage a local region. That combination matters. A newly discovered object is large enough to be consequential. Its orbit is not yet well defined, and the first calculations point toward a specific future date. Planetary defense systems are designed for exactly this kind of case. They do not wait for certainty. They increase observations, refine the orbit, share updates openly, and let the risk estimate move as the evidence improves. In the case of 2024 YR4, that evidence comes from ground-based telescopes at first, and later from the James Webb Space Telescope, whose sensitivity helps constrain both the object's size and its future path when the asteroid becomes extremely faint. The scientific response is therefore measured rather than dramatic. The object becomes important because it tests the machinery of global monitoring in real time. Another lesson lies in the circumstances of discovery. The asteroid is first reported only after it has already passed its nearest point to Earth on that approach, and ESA explains that it was not detected sooner because it came from the day side of the sky, hidden in the sun's glare. This matters because it shows that asteroid danger is not only about the rock itself, it is also about the geometry of discovery. Some objects approach from directions that ground-based surveys cannot search easily, especially when the bright sky near the Sun overwhelms faint-moving targets. In this way, 2024 YR4 becomes a practical argument for wider survey coverage and for observatories that can work where ordinary night-based searches are weakest. Then the expected resolution arrives. In February of 2025, new observations sharply reduce the remaining Earth impact probability. Soon after, the Earth impact solutions are removed altogether for the 2032 encounter. ESA reports that the asteroid falls from level 3 to level 0 on the Torino Impact Hazard Scale, and no longer requires significant attention. While NASA's public updates likewise track the probability downward as the observing arc grows, by March of 2025 ESA states that astronomers have enough information to rule out an Earth impact in 2032. Later, Webb observations even remove the smaller remaining concern about a lunar impact in that same year. What remains after that is not a threat, but a case study. The asteroid does not become famous because it strikes. It becomes useful because it does not. It shows that planetary defense is not a theater of constant emergency. It is a discipline of detection, orbital refinement, and orderly retirement of false alarms as uncertainty gives way to measurement. This is why 2024 YR4 matters so much within the subject of real impact risk. It demonstrates that an asteroid can rise quickly in public concern without ever becoming a true impending disaster. It shows why discovery circumstances matter, especially when an object approaches from the sunward side and is first seen only after a close pass. It shows why official risk lists must move instead of staying fixed. It shows why international coordination becomes necessary even for modest probabilities when the object is large enough to matter physically. Most of all, it shows that the honest face of asteroid science is provisional. The first answer is often incomplete. The second answer can briefly look worse. The better answer arrives only after more nights of observation, more precise measurements, and more disciplined patience. In that sense, 2024 YR4 offers a calm lesson rather than a terrifying one. Real impact risk is not defined by the loudest moment of uncertainty. It is defined by how uncertainty is reduced, how evidence is shared, and how a possible future strike is steadily turned back into an object moving harmlessly through space. Bennu offers one of the clearest examples of a real asteroid risk that remains extremely small, distant, and carefully measured. It is not a rumor of danger, and it is not a present emergency. It is a known asteroid, a well-observed near-Earth object, and one of the most closely studied small bodies in the solar system. What makes Bennu important is not that it threatens Earth in any immediate way, but that its future orbit has been measured precisely enough to reveal a tiny long-range impact probability stretching into the late 22nd century. In the calm language of planetary defense, this makes Bennu unusual. Most asteroids on risk lists appear briefly while their orbits remain uncertain, then disappear as new observations remove the impact solutions. Bennu is different because the risk does not arise mainly from poor discovery data. It arises from a known future close approach to Earth in the year 2135, when Earth's gravity will slightly reshape Bennu's later path. That is why Bennu belongs in this part of the story. It shows how real impact risk can be scientifically genuine while still remaining very small. Bennu is roughly 0.5 kilometer wide, large enough that an impact would matter on a scale far beyond a small local event. It is also dark, carbon-rich, and physically complex, the kind of asteroid that preserves old solar system material rather than appearing as a simple bare rock. NASA's OSIRIS-REx mission transformed knowledge of Bennu by orbiting it, mapping it, touching its surface, and returning samples to Earth. That mission does more than reveal Bennu's geology. It also improves understanding of Bennu's motion. In asteroid risk analysis, physical knowledge and orbital knowledge are not separate for long. The way an asteroid absorbs sunlight and re-radiates heat can slightly alter its orbit over time, especially for a body of this size, for Bennu. This subtle thermal effect matters enough that the mission's detailed measurements help sharpen the long-term forecast. The result is a picture of risk that is not speculative in the loose sense. It is probabilistic, but grounded in close observation. The key moment in Bennu's future is the close pass in 2135. During that encounter, Bennu is expected to miss Earth, but not by such a great margin that the planet's gravity can be ignored. Earth will bend the asteroid's path slightly. That bending matters because after the flyby, Bennu will not continue on exactly the same orbit it had before. Instead, its later route will depend delicately on the details of the encounter. If Bennu passes through certain very small regions of space during that flyby, often called gravitational keyholes, the new orbit created by Earth's pull could set up a later impact on a return encounter in the late 22nd century. This is the long tail of Bennu's risk. The danger does not lie in the 2135 pass itself. It lies in the possibility that the close pass could place the asteroid onto one of a narrow set of future trajectories whose consequences unfold decades later. NASA's published analysis makes the scale of this risk clear. The cumulative probability of Earth impact through the year 2300 is low, about 570 in 1 million. Within that already small total, the single most significant date is September 24th, 2182, with an impact probability of about 370 in 1 million, or about 1 chance in 2,700. Those numbers are not zero, and that is why Bennu remains important. Yet they are also extremely small, and that is why Bennu is not treated as a present crisis. The value of this case lies in precision. Bennu shows that planetary defense can quantify a genuine long-range hazard without exaggeration. Science does not need certainty to be honest. It needs disciplined probability, clear dates, and enough knowledge of the orbit to state both the risk and its smallness at the same time. There is something especially instructive in the calmness of this example. Bennu is not a newly discovered object with a poorly known path. It is one of the best characterized hazardous asteroids known. The risk remains because long-term orbital prediction is delicate when future close encounters with planets are involved. Over decades and centuries, tiny uncertainties can matter. Small non-gravitational forces can matter. Slight differences in position at the time of a flyby can matter. The future therefore becomes a branching structure of possibilities rather than a single rigid line. Bennu's long tail is the scientific expression of that branching. Earth is safe from Bennu for the near future. But late in the 22nd century, a small family of allowable futures still contains impact paths. That is not the same as saying Bennu is on its way. It is better understood as a map of rare but not impossible outcomes created by a known future gravitational encounter. This case also clarifies the meaning of real impact risk. Real risk does not always mean a dramatic probability attached to the next few years. Sometimes it means a very small but physically meaningful chance spread across a longer horizon, attached to an asteroid large enough to matter, and studied well enough that the numbers have scientific weight. Bennu is one of the few objects that fits this description so cleanly. It is not famous because it is the likeliest impactor in an immediate sense. It is famous because it shows how subtle the boundary can be between security and concern when orbital mechanics are followed far into the future. One close pass in the next century slightly reorganizes the possibilities of the century after that. Between those dates lies the patient work of continued tracking and improved modelling. So Bennu stands as a measured warning rather than an alarming one. It is large, dark, ancient, and unusually well studied. It will pass Earth safely in 2135, yet that safe passage is itself the reason for later attention, because Earth's gravity will help decide which future Bennu follows afterward. The tiny probabilities published by NASA do not invite fear, they invite precision. Bennu teaches that asteroid danger can be real without being large, and important without being immediate. In the quiet mathematics of planetary defense, that is enough to make it one of the most instructive objects in the sky. Apophis becomes famous because it shows how a dangerous asteroid can be rewritten by knowledge. When it's discovered in late 2004, the early observations are limited and the uncertainty in its orbit is still wide enough to permit alarming futures. Among those futures are possible impacts with Earth in the years 2029 and 2036. For a brief time, Apophis stands apart from other newly discovered asteroids because the calculated risk is high enough to attract global attention. It rises on the Torino scale, the public hazard scale used to describe impact concern, to a level never previously reached by a newly found asteroid. In that early moment, Apophis appears to embody the classic fear of planetary defense: a large near-Earth asteroid, a specific date, and a non-zero chance of collision within the lifetime of people already living. The object does not become important because it is the largest known asteroid. It becomes important because uncertainty briefly permits an impact that later observation may either confirm or remove. This is the first lesson of Apophis. The dangerous asteroid is often born in the mathematics of incomplete knowledge, rather than in a visible rush toward Earth. The asteroid itself is only one body following its orbit around the Sun. What changes public meaning is the width of the uncertainty surrounding that orbit. In the first stage of discovery, the object is known through a short arc of observation. That means the future is represented not by one narrow line, but by a spread of possible lines. Some of those lines pass close to Earth. A few, at first, pass through it. That is enough to create a real impact concern, even if later evidence will show that the concern is temporary. Apophis is large enough to justify such concern. It is not a small body that would simply vanish in the upper atmosphere. It is an asteroid of substantial size, large enough that an actual impact would matter on a regional scale. That physical significance helps explain why it remains in public memory long after the impact solutions are removed. Yet the deeper importance of Apophis lies in how those solutions are removed. Night after night, and year after year, astronomers continue to observe the asteroid. Each new measurement narrows the uncertainty. The broad cloud of possible futures becomes thinner. Some feared dates disappear first, others remain under study longer. In this way, Apophis changes from an apparent threat into a demonstration of how planetary defense actually works. The year 2029 becomes the central pivot in this rewriting. Early calculations suggest that Earth and Apophis may come together in a way that could still leave danger open for later years. The close approach itself is real, but impact is eventually ruled out. What remains scientifically important is that Earth will still pass close enough to alter the asteroid's orbit through gravity. That means the 2029 encounter is not only a moment of reassurance, it is also a test of prediction. If the path during that pass were poorly known, then tiny differences in position could matter for what happens afterward. This is why Apophis remains an object of close study even after the first dramatic fears begin to fade. For a time, the year 2068 also remains part of the conversation. It represents the long tail of concern, a possible future impact created not by direct collision in the near term, but by the subtle reshaping of the orbit during close planetary encounters. This pattern resembles, in a broader way, the logic seen in other long-range asteroid cases. A safe close pass can still matter because it changes the geometry of later returns. Apophis therefore teaches that planetary defense is not concerned only with direct straight-line danger. It is concerned with repeated motion, future gravitational encounters, and the narrow pathways through which later risk can emerge from earlier safety. Then the rewriting becomes final. Additional optical observations and radar measurements improve the orbit enough to close the remaining doors. One by one, the feared impact years are removed. The asteroid leaves the formal risk lists. Official analyses conclude that Earth is safe from Apophis for at least the next century. This is the point where the public image of the asteroid and the scientific image separate most clearly. In memory, Apophis often remains the asteroid that nearly hit Earth. In science, it becomes the asteroid that showed how serious early concern can be resolved by better data. Its importance does not end when the risk disappears. In a way, that is when its greatest value begins. Apophis therefore stands as a rewritten object in two senses. Its orbit is rewritten by improved measurement, and its meaning is rewritten by the correction of public fear. What begins as a probable danger becomes a case study in orbital refinement. What begins as a symbol of impact anxiety becomes a demonstration of the discipline, patience, and transparency of modern planetary defense. The asteroid itself does not change character in any dramatic physical way. The change occurs in human knowledge. The rock remains what it always is, moving through space under gravity and sunlight. What shifts is the boundary between what is feared and what is known. There is also a deeper calm inside this story. Apophis shows that real asteroid danger is not best understood through permanent alarm. It is better understood through revision. Science does not fail when an asteroid first appears threatening and later proves safe. Science succeeds by allowing the first answer to remain provisional until stronger evidence arrives. In that sense, Apophis becomes a lesson in method. The first orbit is not the final orbit. The first probability is not the final probability. The first fear is not the final truth. Each new observation changes the balance between possibility and certainty. And in the case of Apophis, the long process ends in safety. So this asteroid remains one of the most instructive objects in the solar system, not because it still threatens Earth, but because it no longer does. It carries the memory of how impact risk can briefly seem sharp, specific, and frightening, then dissolve under disciplined observation. The story of Apophis is not the story of a collision avoided at the last moment. It is the story of a risk rewritten over years of careful watching until the feared future is no longer part of the allowed orbit at all. In the quiet record of planetary defense, that outcome matters as much as any dramatic encounter. It shows that the most dangerous asteroid may sometimes become most valuable when it teaches exactly why danger has faded. An asteroid's orbit determines whether it can ever matter to Earth, but orbit alone does not determine what kind of danger it carries. Two asteroids may travel on paths that appear similarly concerning and still differ greatly in what they would do if they ever reached the planet. This difference comes from the asteroid's own physical nature. Size is the first and most obvious factor, yet it is only one part of a larger picture. Density, internal strength, structure, Composition, shape, and surface character all influence how much mass the body contains, how it responds to stress, and how much energy it can deliver in a destructive encounter. In this sense, danger is not written only in the path through space. It is also written in the material character of the object itself. Size matters because volume grows rapidly as a body becomes wider. A modest increase in diameter can mean a much larger increase in total mass if the density remains similar. Since the energy of an impact depends strongly on mass and speed, a larger asteroid generally carries much greater destructive potential than a smaller one approaching at comparable velocity. This is why planetary defense pays close attention to approximate diameter, even when other properties remain uncertain. A body tens of meters across belongs to one level of concern. A body hundreds of meters across belongs to another. A body measuring kilometers in diameter belongs to a different scale again. The shift is not gradual in human terms, it is transformative. The physical consequences of impact change markedly as size rises. Yet size alone can mislead. A large asteroid made of more porous, less dense material may contain significantly less mass than a smaller but denser one. Density describes how much matter is packed into a given volume. In practical terms, it tells how heavy the asteroid truly is for its size. A dark carbon-rich asteroid may be relatively low in density, especially if its interior contains many voids or loosely packed fragments. A stony asteroid may be denser. A metal-rich asteroid may be denser still. These differences matter because an asteroid's destructive potential is not simply a matter of width seen through a telescope. It depends on how much substance is actually present inside that visible outline. Internal strength matters in a different way. Some asteroids are more coherent, with stronger bonding between their constituent materials. Others are weaker and more fractured. A stronger body resists stress more effectively. A weaker body may crack, distort, or shed material more easily under tidal forces, rotation, or sudden pressure. This does not make the weaker asteroid harmless. It makes it physically different. A body with high internal strength behaves more like a single resistant mass. A body with low internal strength behaves more like a compromised structure whose parts do not hold together as firmly. In a hazardous context, that difference affects how the asteroid responds as forces act upon it. Structure is therefore one of the most important and least intuitive properties. Some asteroids appear to be monolithic, meaning they behave roughly like single pieces of rock or metal. Others are rubble piles, which means they are not one continuous solid object but loose assemblies of boulders, stones, dust, and fragments held together mainly by their own weak gravity. From a distance, both kinds may appear as single bodies. Up close, they can be profoundly different. A rubble pile asteroid may contain substantial empty space between pieces. It may have a lumpy shape, a surface strewn with blocks, and an interior that redistributes stress in a very different manner from a solid rock. This changes how the body spins, how it evolves over time, and how it would react under sudden forces. Porosity, the presence of internal empty space, adds another layer to the danger. A porous asteroid can absorb and redistribute energy differently from a compact one. It may be larger than expected for its mass. It may also respond differently to any force that attempts to break, deflect, or compress it. In effect, the asteroid's visible boundary may conceal a much lighter and more fractured interior than simple appearance suggests. This is one reason why exact risk assessment cannot rely only on brightness and orbit. The same apparent diameter may correspond to very different physical realities. Composition further deepens the contrast between bodies. Some asteroids are dominated by silicate rock. Some contain more carbon-rich material, often darker and more primitive in chemical character. Some include substantial metal, especially iron and nickel. These categories are not merely labels of chemistry. They help describe reflectivity, density, heat behavior, and surface evolution. A metal-rich body reflects and stores energy differently from a darker carbon-rich one. A carbon-rich asteroid may be more fragile or more porous in some cases, while a metal-rich body may be denser and more resistant, even within the same broad class. However, variation remains large. Real asteroids are not laboratory spheres made of uniform matter. They are weathered remnants of formation, breakage, heating, and collision, each with its own layered history. Shape also matters more than it first appears to matter. Many asteroids are irregular, elongated, flattened, or bilobed. Their gravity is weak and their forms preserve the history of collisions and reaccumulation. An oddly shaped asteroid rotates in a more complex way than a nearly round one. Its surface heats unevenly in sunlight. Its mass is not distributed evenly around its center. These facts influence how its orbit can change slowly over time and how it reacts to torque, stress, and external disturbance. Even danger, in the broad physical sense, is partly shaped by form. Rotation adds still more complexity. Some asteroids spin slowly and steadily, others rotate faster, and some may tumble rather than spin around one stable axis. Rapid rotation can reveal something about internal strength. A loose rubble pile cannot usually spin beyond certain limits without shedding material, while a stronger monolithic body can endure faster turning. Rotation also affects how sunlight warms and cools the surface, which over long times can alter orbital motion slightly. The body is therefore not just a mass moving through space. It is an active physical object with texture, motion, and internal constraints. This is why two asteroids on similar paths can still represent very different kinds of danger. One may be smaller but denser. One may be larger but weaker. One may be compact and strong. Another may be porous and loosely bound. One may carry a darker surface that hides its true size. Another may reflect more light and seem larger or smaller than it truly is until better measurements are made. Real hazard emerges from the combination of orbital geometry and material character. The path decides whether Earth and asteroid can meet. The body decides what that meeting would physically mean. So this region of the subject is one of hidden nature. The dangerous asteroid is not only a point on a chart or a probability on a list. It is a real object made of matter with specific physical properties that shape its potential consequences. Size opens the first distinction. Density refines it. Strength and structure alter it further. Composition gives each asteroid a different material identity. Shape and rotation reveal how that identity behaves in motion. The most dangerous asteroids are therefore not simply those that come near Earth, but those whose physical nature turns orbital possibility into meaningful destructive power. When an asteroid passes close to Earth and does not strike, the encounter can still matter greatly. In some cases, it matters more than a simple distant passage, because the planet's gravity can bend the asteroid's path and alter the shape of its future orbit around the Sun. This is the region where asteroid danger becomes especially delicate. The object survives the encounter. Earth survives the encounter. Nothing burns in the atmosphere. Nothing strikes the surface. Yet the geometry of the past can quietly reorganize the future. A safe approach is not always the end of concern. Sometimes it is the event that decides which later futures remain possible. Gravity acts across distance, not only at the moment of contact. As an asteroid approaches Earth, the planet begins to pull on it more strongly than it does when the object is far away. The closer the pass, the greater the change in the asteroid's motion can become. Usually the object arrives on a solar orbit and leaves again on a new solar orbit, still bound mainly to the Sun. What changes is the direction and speed of its motion relative to the planet during the encounter. The pass behaves like a gravitational turning point. The asteroid falls inward, curves around Earth's moving gravitational field, and departs on a slightly altered route. This bending is not random. It depends on geometry, the exact incoming direction of the asteroid, the speed of approach, the distance of closest passage, and the orientation of the orbit all shape the outcome. A small difference in the path before the encounter can produce a noticeable difference in the path after it. This is why close approaches are studied with such precision. For a distant object, uncertainty in position may matter only modestly. For an asteroid about to pass near Earth, that same uncertainty can decide whether the outgoing orbit remains harmless or becomes one that deserves renewed monitoring. The most delicate part of this geometry is often described through the idea of a keyhole. A gravitational keyhole is a very small region in space near Earth such that, if the asteroid passes through it during a close encounter, Earth's gravity bends the orbit by just the right amount to set up a later impact on a future return. The object does not hit Earth during the first pass. Instead, the first pass becomes the condition for a later collision. The keyhole is therefore not a physical opening or visible corridor. It is a mathematical region defined by timing, trajectory, and the way a bent orbit matches Earth again after one or more revolutions around the Sun. This idea reveals how fine asteroid danger can become. Earth is large on human scales, but in orbital calculations a future impact can depend on whether an asteroid passes through a region in space that may be only a few hundred meters wide. If the asteroid misses that keyhole, then the later impact path is not created. If it passes through, the new orbit may bring it back to the same place at the same time as Earth years or decades later. In this way, danger becomes a matter of very small positional differences acting through very large spans of time. The keyhole concept also clarifies why close pass predictions are often refined so intensely. Scientists are not only asking whether the asteroid will hit Earth on the upcoming date, they are also asking whether the asteroid will pass near any of the tiny regions that could create risk later. This requires extremely accurate knowledge of the orbit before the encounter. It also requires careful modelling of Earth's gravity, the gravitational pull of other bodies, and in some cases even tiny non-gravitational forces such as the slow thermal push caused by sunlight. The geometry of the pass depends on relative motion as much as on distance. Earth is moving around the Sun. The asteroid is moving on its own orbit. During the encounter, the planet is not waiting in stillness for the asteroid to arrive. Both bodies are in motion, and the asteroid passes through a changing gravitational environment created by a planet that itself is advancing along its orbit. The outgoing path therefore reflects not only how close the asteroid comes, but also how the entire encounter unfolds in moving space. The real event is a timed three-dimensional passage, not a flat crossing of lines. There is also an important difference between a merely close pass and a truly transformative one. Many asteroids pass Earth at safe distances that produce only minor orbital adjustments. These changes may be measurable, but they do not reorganize the future in any dramatic way. A much closer pass, however, can shift the orbital period enough that future returns happen on different dates. Even a small change in orbital period matters because Earth also returns to each place in its orbit on a yearly cycle. If the asteroid's new period creates a resonant timing relationship with Earth, then future encounters may become more concentrated. This is how one safe passage can prepare the geometry for another. For this reason, A close approach often marks a hinge in the asteroid story. The orbit before the encounter and the orbit after the encounter belong to the same body, but they do not always present the same level of concern. Planetary defense therefore treats such dates as decision points. Before the pass, astronomers try to shrink the uncertainty as much as possible. During and after the pass, new measurements reveal which path the asteroid actually follows. Once the encounter is complete, many hypothetical futures can be removed at once because the outgoing orbit is no longer guessed, it is observed. A feared future impact may vanish at that moment. So this region of real impact danger is not a region of collision itself, but of orbital leverage. Earth's gravity becomes a quiet sculptor of future possibilities. A close pass that appears safe can still be one of the most important moments in the life of a hazardous asteroid because it is capable of redirecting the path just enough to matter later. The keyhole is the purest expression of this delicacy. It is a tiny region, invisible and temporary, inside a vast space where nearly every path is safe but a few narrow ones are not. To understand dangerous asteroids fully, one must understand this geometry of survival, because the most consequential encounter is sometimes the one that misses Earth and, by missing in exactly the right way, decides what the asteroid may become on its next return. When a hazardous asteroid finally reaches Earth's immediate environment, it does not meet the ground first, it meets the atmosphere. This meeting is the first physical collision between the incoming body and the planet, and it changes everything. Space offers almost no resistance. The atmosphere offers enough. Even though air is thin at high altitude, an asteroid arriving from space moves so fast that the encounter with those upper layers begins to compress, heat, and stress the body long before any surface is involved. For smaller asteroids, this atmospheric passage becomes the entire event. The object never survives to strike the ground. It burns, fragments, and releases its energy overhead. In this sense, the sky itself becomes Earth's first protective layer. The crucial fact is speed. Near-Earth asteroids approach Earth at many kilometers per second, far faster than any ordinary aircraft or weather system. At such velocities, the problem is not simple friction in the everyday sense. The air in front of the asteroid cannot move aside gently enough. It is violently compressed. Compression raises temperature. The gas ahead of the body becomes extremely hot, and that heat then affects the asteroid's surface. The outer layers begin to melt, vaporize, and erode away. This process is called ablation. Ablation means the gradual stripping of material from the surface as intense heating removes it. Light appears because the hot gas and the heated material radiate strongly during the passage. The atmosphere does not act evenly on every asteroid. Size matters at once. A small incoming body has relatively little mass compared with its surface area, so heating and erosion can affect a large fraction of it quickly. A larger body carries more mass inward and may resist complete destruction for longer. Composition matters as well. A strong iron-rich body can endure atmospheric stress differently from a weaker stony or porous one. Structure matters no less. A fractured rubble-like asteroid may begin to fail under pressure more readily than a coherent body. Atmospheric entry is therefore not a single script repeated each time. It is a contest between the incoming object's physical nature and the rapidly increasing stress imposed by air. As the asteroid descends, the air grows denser. This increases both heating and mechanical pressure. The pressure does not act only on the front surface. It can penetrate cracks, weak zones, and internal boundaries inside the body. If the stress exceeds the internal strength of the asteroid, fragmentation begins. Fragmentation is often more important than heating alone. Once a body breaks into pieces, the total exposed surface area rises sharply. More surface means more rapid ablation. The fragments slow more effectively, heat more effectively, and often begin to separate into a widening trail. What had been one incoming object becomes a chain or cloud of smaller ones, each now easier for the atmosphere to punish. This is why many asteroid events end not with a crater, but with an airburst. An airburst is an explosion-like release of energy in the atmosphere caused by sudden fragmentation and rapid deceleration. The asteroid does not detonate like a manufactured weapon. Instead, the structure fails. The fragments dump kinetic energy into the surrounding air, and the atmosphere responds with a powerful shock wave. The result can be a flash, a loud pressure wave, and widespread damage below even when no large fragment reaches the surface. The danger comes from the conversion of the motion into heat and pressure high above the ground. Brightness during entry can be deceptive. A spectacular fireball does not necessarily mean a large surviving asteroid is on its way to the ground. Often it means the opposite. The object is losing mass rapidly and pouring energy into the air. The visible glow comes from the heated gas, ionized material, and ablated debris. The most dramatic visual phase may coincide with the body's destruction rather than its survival. What looks most violent to an observer may be the moment Earth's atmosphere is doing its most effective work. Deceleration also plays a major role. In space, the asteroid keeps nearly all of its incoming speed. In the atmosphere, drag begins to steal that speed away. Drag is the resisting force exerted by the air as the body moves through it. For a small object, enough deceleration can occur that any surviving fragments lose much of their original cosmic velocity before lower altitudes are reached. This greatly reduces the energy available later. Larger objects, however, can carry enough momentum that the atmosphere cannot slow them completely before major energy release occurs. The balance depends on mass, speed, angle of entry, and physical strength. A steep entry compresses the event into a shorter path through the air. A shallower entry spreads the encounter across a longer path, giving the atmosphere more distance over which to act. Altitude matters because the same release of energy has different consequences depending on where it happens. A high breakup spreads much of the event through thinner air and wider distance. A lower breakup concentrates the shock more strongly into denser air. The asteroid reaches that point when aerodynamic stress, heating, and internal weakness finally overcome its structure. Some bodies fail high and early. Others hold together deeper into the atmosphere. The atmosphere is not a simple wall. It is a graded medium, and each asteroid penetrates it differently. The atmosphere therefore acts both as shield and filter. It removes the smallest bodies almost completely. It weakens and fragments many larger ones. It converts some incoming asteroids into airbursts rather than ground strikes. Yet it does not erase danger altogether. Its protective role is real, but conditional. The same air that destroys an incoming body can also transmit the resulting shock downward. Protection and hazard are intertwined in the entry process itself. So this atmospheric region is the first true battleground between asteroid and planet. The body arrives from silence into resistance. Speed compresses air into heat. Surface material erodes away. Pressure invades cracks and weakens structure. Fragmentation multiplies the surface exposed to destruction. Light flares. Fragments spread, and motion is surrendered to the atmosphere as shock and heat. Many dangerous asteroids end here, not because they are harmless, but because Earth's air is deep enough and forceful enough to break them before any crater can form. The sky absorbs the first blow by turning the energy of the fall against the falling body itself. If an asteroid survives the atmosphere and reaches the surface with enough speed and mass, the nature of the danger changes again. The sky no longer absorbs the event. The ground or the ocean receives it. At this stage, impact location becomes one of the most important facts in the whole chain of risk. NASA's impact assessment work treats surface hazards differently for land and ocean cases because the dominant effects are not the same. For land impacts, the main local dangers are destructive blast waves and thermal radiation, together with crater formation and related ground damage. For ocean impacts, the central regional danger becomes tsunami generation, shaped by how the water cavity forms and how waves later move toward shore. The same incoming asteroid can therefore produce very different consequences depending only on where it arrives. On land, the first defining act is excavation. A high-speed impact does not behave like an ordinary falling rock striking soil. The kinetic energy is so large that both the asteroid and the target ground are suddenly compressed, shocked, and displaced. A crater forms as material is blasted outward and upward from the impact point. This is why cratering belongs among the recognized immediate hazards of asteroid impacts, alongside overpressure, wind blast, thermal radiation, ejecta deposition, and tsunami. The crater is not merely a hole left behind after the damage. It is part of the damage process itself, because excavation throws out material, reshapes the terrain, and marks the place where a large fraction of the incoming energy is delivered directly into the ground. Yet the crater is often not the most far-reaching effect for people beyond the immediate point of impact. NASA's hazard assessments emphasize that local ground damage from land impacts is strongly driven by blast overpressure and thermal radiation. The impact or low-altitude terminal event creates a powerful outward-moving pressure wave that can break windows, damage or collapse structures, and flatten built environments depending on distance and energy. Thermal radiation, the intense flash of heat emitted during the event, can burn exposed surfaces and ignite materials close enough to the source. In practical terms, a land impact is dangerous across a surrounding region where shock and heat travel outward from the point of contact. This is why land impact can be so concentrated and so severe. The solid surface couples the energy of the event into one fixed place where the atmosphere, the fireball, the pressure wave, and the crater all reinforce the local destruction. Ejecta, the material thrown out by excavation, adds another mechanism of harm near the impact zone. Seismic shaking can also occur, though studies of immediate hazards generally find that blast and thermal effects are the more important killers in many modelled cases. The result is a layered surface event. Closest to the centre lies excavation and devastation. Farther out lies a region where shock and violent winds break structures and injure people. Ocean impact rearranges this pattern. The incoming body still delivers enormous energy, but now the first target is water, rather than rock or soil. NASA impact models treat this differently, because the remaining kinetic energy at the surface creates an initial water crater or cavity, rather than a permanent excavated hole in solid ground. That cavity quickly collapses and transfers energy into waves. The physics is therefore less about a fixed crater left in place, and more about the motion of displaced water. The danger does not remain concentrated only at the impact point. It begins to travel. This travelling danger is the asteroid-generated tsunami. In NASA's hazard framework, regional damage from ocean impacts is assessed mainly through the waves produced by the water strike and their later inundation at shore. The wave created in deep water does not remain in the same form as it moves. As it approaches shallower coastal regions, it changes through shoaling, which means the wave grows in height as the water depth decreases. Local topography then becomes crucial. The exact coastline, the slope of the seafloor, and the shape of bays or low-lying land all influence how much flooding occurs when the water comes ashore. Ocean impact is therefore not one simple wall of water spreading equally in every direction. It is a process that begins at sea and expresses its danger fully only when geography translates wave motion into inundation. Even so, ocean impact is not automatically worse than land impact. This is one of the quieter findings in modern hazard studies. Research comparing different impact effect finds that average impacts over land are generally more dangerous to human populations than average impacts over water. Even though water impacts can generate tsunami, one reason is simple geography. Much of the open ocean is far from dense population. Another is physical. The largest immediate killers in many impact scenarios are still the aerothermal and blast effects associated with entry and impact, and these tend to matter most when people are close to the event. Water can spread danger across great distance, but it also often places the primary energy release far from where most people live. That does not make ocean impacts mild. A tsunami can be the dominant hazard for deep water strikes, and it can threaten coastlines over broad regions if the impact is energetic enough and the geometry favors shoreward flooding. NASA's older planetary defense analyses also note that ocean impact damage associated with tsunami can peak for objects around a few hundred meters in size, because smaller bodies may not reach the surface with enough cosmic speed and energy to drive the most consequential water effects. The important point is that the ocean changes the form of the catastrophe. Instead of one excavated center surrounded mainly by land blast and heat, the event becomes a displaced water problem whose most important injuries may occur later and far from the point where the asteroid first hits. So land and ocean impacts wound the planet in different ways. Land impact concentrates energy into excavation, blast, heat, ejecta, and local surface devastation. Ocean impact converts much of that surface encounter into moving water, with regional flooding determined by wave propagation and the shape of the coast. In both cases, the atmosphere is no longer the final barrier. The asteroid has reached the surface and forced the planet to answer physically. But the answer depends on what kind of surface receives it. Earth is one world with two dominant surface realms, and a dangerous asteroid can make those realms behave very differently when the final collision comes. Only the rarest and largest asteroid impacts extend their danger far beyond the atmosphere, the surface, and the immediate region of blast or tsunami. In these uncommon cases, the strike affects the planet as a climate system. The damage no longer belongs only to the place where the asteroid arrives. It rises into the sky, spreads across continents and oceans, and alters the flow of light, heat, water, and life. This is the region sometimes described as impact winter. The phrase refers to a period in which material lofted high into the atmosphere reduces the sunlight reaching the ground and disturbs the normal balance of climate and biology. The local strike becomes a planetary aftermath. The key change is altitude and persistence. A smaller impact may throw dust and debris into the lower atmosphere, where much of it settles or washes out comparatively quickly. A very large impact can inject enormous quantities of fine material into the upper atmosphere, where removal is slower and the particles can spread around the globe. Dust from pulverized rock, droplets condensed from vaporized target material, soot from widespread fires, and sulfur-bearing aerosols formed from sulfur-rich rocks can all contribute to this veil. Their exact relative importance remains under study, and the balance depends strongly on the size of the impact and on the geology of the place that is hit. Once this material reaches the upper atmosphere, sunlight is no longer transmitted in its ordinary way. Some light is reflected back to space, some is scattered, some is absorbed aloft before it can warm land and sea below. The result is dimming at the surface and cooling near the ground, even while parts of the upper atmosphere may warm because suspended particles absorb solar energy there. The skies become darker, while the structure of the atmosphere itself becomes less familiar. Cooling matters because nearly all large food systems depend, directly or indirectly, on photosynthesis. Plants on land and microscopic photosynthetic organisms in the oceans require sunlight to support the food webs above them. If sunlight is cut sharply for long enough, this primary productivity declines. Growth weakens. Harvests fail. Marine food chains begin to contract from their base. The climate effect is therefore not only a matter of temperature, it is also a matter of biological energy. A planet can remain physically intact and still suffer severe ecological damage if enough light is withheld for enough time. The water cycle also changes. A colder surface generally means weaker evaporation, altered cloud patterns, and disrupted rainfall. In some regions, this may mean drier conditions. In others, it may mean seasonal shifts unlike those to which local ecosystems are adapted. The exact regional outcome depends on circulation, geography, ocean response, and how long the atmospheric veil persists. Yet the broad principle remains clear. A very large impact can alter not only how much sunlight reaches the ground, but also how moisture moves through the atmosphere. Agriculture suffers under both reduced light and disturbed rainfall. The largest known example in Earth history is the Chicxulub impact at the end of the Cretaceous period. It matters here as the clearest evidence that an asteroid impact can produce global climatic consequences. Research indicates that the impact lofts immense quantities of fine material and climate-active gases into the atmosphere. Sunlight falls sharply, surface temperatures decline, photosynthesis is suppressed, food webs on land and in the oceans undergo catastrophic collapse. Many details of the exact mechanism remain under study, especially the relative roles of dust, soot, and sulfur-rich aerosols. But the broad scientific picture is stable. A sufficiently large impact can darken and cool the planet enough to help drive mass extinction. Impact site matters enormously. The same asteroid striking a different kind of crust does not necessarily produce the same climate response. If sulfur-rich sedimentary rocks are vaporized, the resulting aerosols may strengthen cooling. If hydrocarbon-rich target rocks and widespread ignited biomass produce more soot, the atmospheric darkening may also intensify. If the target is less favorable to lofting such material, the global aftermath may be less severe even when the impact is still immense. This means that planetary danger at the larger scale is not determined only by the asteroid. It is determined by the collision between asteroid and planet, including what kind of surface is struck and what material is injected into the sky. Time then becomes part of the disaster. A blast wave passes in minutes. A tsunami may arrive over hours. A climate perturbation unfolds over months and years. The first darkness may be followed by prolonged cooling, ecological stress, and failed recovery across growing seasons. Ocean ecosystems may respond on their own timescales, with disruptions to plankton and food chains extending beyond the initial atmospheric phase. Human civilization, if exposed to such an event today, would not experience it as one single catastrophe, but as a sequence of shortages, crop losses, and international strain driven by the same dimmed sky. This is why the rarest large impacts differ from the smaller but more frequent hazardous asteroids discussed earlier. The smaller events can devastate a city, a region, or a coastline. The largest events can stress the operating system of the whole planet. They do so by transforming solid Earth into atmospheric burden. Rock becomes dust. Target minerals become aerosols. burned landscapes become soot. The atmosphere, which earlier protects Earth by destroying many incoming bodies, now becomes the medium that carries the aftermath everywhere. Even here, science remains careful. Not every kilometre-scale impact produces the same climate response, and the precise severity depends on particle size, injection height, target composition, and how long the suspended material remains aloft. Current research continues to refine these variables. Some studies emphasize fine dust, others highlight sulfur-bearing gases or soot from widespread fires. The uncertainties concern emphasis and exact duration more than the central conclusion. The central conclusion is that the largest impacts can reduce sunlight, cool the surface, disrupt rainfall, weaken photosynthesis, and impose a planetary food crisis long after the crater forms. So this inner region of asteroid danger belongs to aftermath rather than impact itself. The strike is over, yet the true scale of the damage is only beginning to unfold. Dust and aerosols spread through the atmosphere, light fades at the surface, temperatures fall. Rain patterns shift, fields, forests, and oceans lose part of the energy on which they depend. A local collision becomes a global dimming. In the rare worst cases, that dimming becomes one of the most severe natural disruptions a planet can endure. Not because the impact remains visibly active, but because the sky continues to remember it. At the innermost layer of real asteroid danger, the subject turns away from the asteroid itself and toward the human response. This is the region of warning and deflection, where the most important fact is not strength, speed, or crater size, but time. A dangerous asteroid becomes far less dangerous if it is found early. A body discovered only shortly before arrival offers little room for action. A body discovered years or decades in advance can be tracked, understood, and, if necessary, diverted. This is why modern planetary defense begins not with heroic last-minute intervention, but with patient search. Warning is the first defense. Deflection becomes possible only because warning comes first. Detection begins with repeated watching of the sky. Survey telescopes scan large areas night after night, looking for faint points of light that move against the far steadier background of stars. This work is quiet and systematic. A newly found asteroid is first just a track of positions measured across time. From those positions, astronomers compute an orbit. Then the orbit is checked again with more observations, and again after later returns. Warning grows through repetition. The asteroid is not made safer by being observed, but human knowledge of it becomes more exact. Uncertainty shrinks. False impact solutions disappear. Real long-term concerns become clearer. Ground-based surveys remain the foundation of this work. They discover most near-Earth asteroids now known, and they continue to refine the census of the inner solar system. Yet ground-based detection has limits. Telescopes on Earth are constrained by daylight, weather, the brightness of the moon, and especially by the geometry of objects that approach from the direction of the sun. Some asteroids remain difficult to find because they spend much of their time in glare-filled parts of the sky. This is one reason planetary defense places such importance on space-based survey work. A telescope beyond Earth's surface constraints can search more effectively for darker bodies, and for objects whose thermal glow reveals them even when visible light does not. This is the purpose of NEO Surveyor, NASA's dedicated planetary defense space telescope. It is designed not primarily to visit asteroids or to image them for beauty, but to find them before they find Earth. By working in infrared light, it can detect the heat emitted by asteroids rather than relying only on reflected sunlight. This matters because dark asteroids can be physically large while reflecting little light, and because infrared observations help estimate size more reliably. In practical terms, such a mission strengthens the earlier stage of defense. It increases the chance that dangerous objects will be found sooner and characterized better. Detection is often less dramatic than deflection, but in planetary defense it is the deeper achievement, because the best asteroid impact is the one prevented long before emergency conditions ever arise. Warning also depends on coordination. One telescope alone does not protect a planet. Discovery must be followed by confirmation from other observatories, by orbit calculation, by risk assessment, and by sustained international communication. Planetary defense is therefore not a single instrument or single mission. It is a network of surveys, follow-up telescopes, orbit analysts, radar work when possible, and public agencies that compare results and issue updates. The object moves through one sky, but the response is distributed across many nations and many institutions. This shared vigilance is part of what makes the field calm rather than theatrical. No single observatory carries the whole burden. Protection grows through accumulation of observations and through agreement on what those observations mean. If warning reveals that a future impact is genuinely possible, and that there is enough lead time, then deflection enters the picture. Deflection means changing the asteroid's orbit slightly so that it misses Earth later. The crucial word is slightly. An asteroid does not need to be blown apart or hurled across the solar system. If action begins early enough, a very small change in speed, applied years before the predicted encounter, can grow into a large misdistance by the time Earth and asteroid would otherwise meet. This is one of the calmest and most important truths in the subject. Planetary defense is not necessarily about overpowering the asteroid. It is often about time multiplying a tiny change. The clearest demonstration of this idea is NASA's DART mission. DART strikes the small asteroid moonlet Dimorphos in a deliberate test of kinetic impact, which means changing an asteroid's motion by hitting it at high speed with a spacecraft. The target is chosen because it poses no danger to Earth, and because its orbit around the larger asteroid Didymos can be measured from Earth. After impact, the orbit of Dimorphos is measurably shortened by about 32 minutes. This is a historic result. It marks the first time human beings deliberately alter the motion of a celestial object. Just as important, the result shows that the transferred effect is not limited to the momentum of the spacecraft alone. Ejected debris leaving the asteroid adds additional thrust, making the deflection stronger than a simple impact calculation would suggest. Yet DART is only the first half of the lesson. To turn one successful demonstration into a dependable technique, the details must be understood more deeply. This is the role of ESA's Hera mission. Hera travels to the Didymos system to examine the aftermath of the DART impact closely, measure the crater and the properties of Dimorphos, and determine exactly how the asteroid responds as a physical body. This matters because deflection is not performed on abstract masses. It is performed on real asteroids with real structures. A strong coherent asteroid and a loose rubble pile asteroid may not react in the same way to the same intervention. Hera therefore transforms a bold demonstration into a more mature science of repeatable planetary defense. There are other theoretical methods of deflection, including long-duration gravitational towing by a spacecraft, or the use of concentrated energy in special cases, but the deepest lesson remains unchanged. Any method depends first on discovery and lead time. The later an asteroid is found, the fewer the useful choices become. The earlier it is found, the more measured and modest the intervention can be. Warning is therefore not separate from deflection. Warning is what makes deflection practical. So the innermost human layer of asteroid danger is neither fear nor impact. It is preparation. Telescopes search, observatories confirm, analysts refine orbits, risk systems compare future paths with Earth's future position. Space missions improve detection and test whether a dangerous orbit can be altered in a controlled way. Neo-Surveyor represents the search for earlier warning. DART shows that orbital change can be real. Hera is meant to reveal how that change truly works in detail. Together they express the most hopeful fact in the subject. Asteroid danger is real, but it is not beyond understanding. If the object is found early enough, the future does not need to be accepted as given. It can be measured, and in some cases it can be changed. Night returns to its ordinary scale after the long chain of danger is understood. The asteroids remain in their distant belts and inward paths. Earth remains beneath its atmosphere, moving through the same orbital space it has always crossed. Most of the time, nothing happens. Most of the time, the dangerous stones of the solar system remain only possibilities, circling the sun in silence while telescopes continue their patient work. That quiet is part of the truth. The threat is real, but it is not constant in the human sense. It belongs to long intervals, careful measurements, and probabilities that usually decline as knowledge improves. In that calm, the planet appears less helpless than it first seems. The atmosphere breaks many small arrivals before they touch the ground. The oceans and continents bear the memory of older strikes, yet they also show how rare the greatest ones truly are. Above all, the human response has entered the story. Eyes watch the sky. Orbits are refined. Risk is reduced from fear into numbers, from rumor into evidence, from sudden alarm into method. The future is not fully controllable, but it is no longer wholly unseen. So the most dangerous asteroids are not only objects of destruction, they are also objects that teach scale, patience, and attention. They remind human beings that the solar system is not empty, not still, and not arranged for comfort. Yet they also show that understanding can widen before catastrophe arrives. A small change made early can prevent a vast event later. A faint point of light, found in time, can become an object of study rather than impact. Earth continues onward beneath the dark, wrapped in air, carrying oceans, weather, cities, forests, and memory. Around it, the ancient stones continue their own long motion. Between those two facts lies the quiet work of watchfulness. And for now that watchfulness holds,